Hello, my name is Hannah.ROMberg and I work at the Institute of Energy Efficient Buildings and Indoor Climate. As a PhD student at RWTH Aachen University, my research focuses on the optimal design and operation of heat pumps. Building energy systems become more complex and diverse these days, making it harder to develop heat pumps under realistic operational scenarios. As a consequence, we use hardware-in-the-loop testing procedures at this institute. The idea is testing real-life hardware in a simulated environment. In our case, we have a real heat pump, which later is then coupled to a simulated building. According to the building simulation, we then set the flow temperature for the heat pump. With our hydraulic test bench, we set a realistic return temperature at the condenser of the heat pump. On the evaporator side, we use the climate chamber to imprint changing weather conditions for the heat pump. This procedure allows us to test new control algorithms and basically bring the field test to our lab. Today, I want to conduct a hardware-in-the-loop experiment with an R290 heat pump for a single-family house. I'll bring you along and we'll first set up the building simulation and then go to the lab and conduct the experiments. Let's go. For our building simulation, we use Modelica. Modelica is an object-oriented modeling language which allows us to dynamically model physical systems. This is our in-house library for dynamic modeling of building energy systems, short BESMOD. The building is divided into several subsystems. The modular design allows us to simulate an entire system or to substitute models with real-life hardware situated in the lab. For this experiment, we focus on the building and its hydraulic system. First, we have to configure some general parameters. Our building is located in Aachen, Western Germany. We therefore choose the corresponding weather data set, which later will be used to condition the climate chamber in the lab. Our house should be equipped with an underfloor heating system. Hence, we set the hydraulic supply temperature at nominal condition to 35 degrees C. For the building itself, we select a pre-configured reference building for the city of Aachen. Let's have a closer look at the hydraulic system. The hydraulic system consists of the submodules control, generation, distribution, and transfer. For the control submodule, we choose an algorithm which controls our heat pump and an electric backup heater. The distribution system consists of no thermal energy storage, since our heat pump only supplies the building loads. Finally, as already mentioned, our single-family house is equipped with an underfloor heating system, hence we choose the corresponding transfer system here. With these configurations done, we are left with the generation part, which is not configured in the simulation here. Our heat pump is set up in the lab and will later be coupled with this simulation. Let's go to the lab and check it out. Welcome to our testing facility. This is our climate chamber. With the help of the air conditioning unit, we can condition temperature and humidity of the air inside the climate chamber. Right in the middle, you see our self-built heat pump. Before we can get the experiments going, we have to take certain safety measures. For that, let's go to the control room. This is our enclosed control room. Because we are working with R290, which is a flammable refrigerant, we have to follow certain safety protocols. We first mark a person working in this laboratory and then change from standby to laboratory operation. This activates our safety system. We have gas sensors all over the lab. If at some point we detect an increased propane concentration, the ventilation system will automatically be activated. In addition, the laboratory doors will open automatically to ensure maximum ventilation. To start the experiment, we first have to turn the climate chamber, the hydraulic test bench and the heat pump on. We want to reach a stable operating point first, before then starting the dynamic experiment. To start our climate chamber, we set the volume flow rate to 3000 cubic meters an hour. The temperature is set to 10 degrees C and we leave the relative humidity at 50%. Now we turn on the control. As a result, we can now observe that the fan is turned on. Because our temperature measured inside the climate chamber is still above our set temperature, we can now observe our cooling circuit cooling down the air inside the climate chamber. Next, we start our hydraulic test bench. We leave the set return temperature at 30 degrees C and set the volume flow rate to 1000 liters per hour. Start the control. And now we can observe on the left that our valves are being opened. Our pump is turned on, and as a consequence, we see the volume flow rate increasing here. Finally, we can turn on our heat pump. We set the compressor frequency to 50 Hz and the fan speed to 10 Hz. We then change the mode to heating mode and can start our heat pump. We see the fan being turned on immediately with a frequency of 10 Hz. The compressor takes a while, but now we see it being turned on. Very nice. Let's have a closer look at the measured data of our test benches. I can watch the measured data in real time on this dashboard. In the upper left plot, we see the set temperature of the climate chamber in blue and the actual temperature in red. For now, we are a little too cold. Scrolling down, we can see temperature and pressure measurements of the refrigerant cycle on the right. On the left, we evaluate different efficiencies for the compressor and the coefficient of performance for the entire heat pump. The experiment is now running for 24 hours. The measurement data is recorded automatically and pushed to a database. I'll have a look at the data tomorrow, and that's it for today.